I want you to picture something for me. You've just walked into a room. It's pitch black. You can't see anything. What is the very first thing your brain does?
It panics.
Well, maybe, but before the panic sets in, it predicts. It predicts where the light switch should be. It predicts where the furniture probably is so you don't, shin kick the coffee table.
Right. We always talk about the brain as this incredible prediction machine.
It's always trying to stay one step ahead of reality.
It wants to minimize surprise. Surprise is dangerous, and prediction is, well, it's safety.
Exactly. But here's the question that kept me up last night after reading this research. What happens when the room keeps changing?
Uh-huh.
What happens when you reach for the light switch and it's not there? And then you reach again and it's on the floor. And then the next time it's on the ceiling.
When the environment stops being polite and predictable.
That is what we are digging into today. We are looking at a fascinating and kind of heavy-hitting paper by Anna Vaskovich and Elizabeth B. Torres from Rutgers.
The title is a mouthful.
It really is. Rethinking statistical learning as a continuous dynamic stochastic process from the motor system's perspective.
Try saying that 5 times fast.
I won't. But the core idea inside this paper, it completely flipped my understanding of what it means to be confused.
I know, right? It argues that the feeling of flailing around, that moment when you have no idea what you're doing, might actually be the smartest mode your brain has.
It's a defense of the flail.
It really is.
So we're going to look at why your brain sometimes needs to ignore the past to learn the future, and why standard science and maybe even modern AI might be getting this wrong.
And to understand why they're getting it wrong, we have to start with this beef the authors have with their own field. They call it the averaging problem.
This part really stuck out to me. Because in most science, averages are good, right? You want the trend line.
Of course. You want to know that on average, this medicine works, or on average, this stock goes up.
But that's not what they're saying here.
Not at all. In neuroscience, specifically in statistical learning, researchers take a ton of data from brain signals, like from an EEG, and they smooth them out. They're looking for the clean pattern.
The signal.
The signal, yeah. And anything that jitters around that line, they just call it noise.
Right, like static on a radio. You just tune it out so you can hear the song.
But Vasevich and Torres are asking a really provocative question here. What if the static is the song?
That's a great line. But what does that mean practically? I mean, if my brain signal is jumping all over the place, isn't that just junk data?
Not necessarily. Think about it like this. If you measured the average temperature of a person over a year, you'd get, what, 98.6 degrees?
Give or take, yeah.
But that average hides the fever you had in February. It hides the hypothermia you risked jumping into a cold lake in July. The average hides the events.
I see.
These researchers argue that by smoothing out the brain data to find that, that normal curve, we are deleting the moments where the actual learning is happening.
We're deleting the struggle.
Precisely. So they decided to look at the gross data. And they don't mean gross as in disgusting. They mean the raw, unfiltered, moment-by-moment fluctuations. They call them micro-movement spikes, or MMS.
Micro-movement spikes. Okay, so we're zooming way in on the jitter.
All the way in. They looked at the tiny peaks and valleys in the brain signal, all the deviations from the average, and instead of treating them as errors to be smoothed over, they treated them as a continuous story.
They wanted to see how the brain's noise changes when the world gets chaotic.
That's it. And to test this, they couldn't just have people sitting in a dark room. They set up a game.
A visual search task.
Yeah, imagine Where's Waldo, but with letters. You're staring at a screen filled with rotated L's, the distractors, and you have to find a rotated T.
And press a button as fast as you can when you see it. Sounds pretty standard for a psych experiment.
The task is standard. The environment, though, that was the trick. They split people into 3 groups to see how their brains handled different levels of uncertainty.
Okay, so group 1.
Group 1 was the correlated group. This was easy mode. The layout of the letters repeated, so if the T was in the top corner, the L's were usually in the same spots.
Got it. So the brain loves that. It's like, I've seen this movie before. I know where to look.
Then you have group 2, the random group, hard mode. Every single trial, the layout changed. Total chaos.
Well, that sounds frustrating.
No pattern to learn whatsoever. You just have to hunt every single time.
And then there's the third one.
The most interesting one, the mixed group. This was the unstable environment. Sometimes the layout repeated, other times it was completely random.
So it was a mix of reliable and unreliable information. You never know what you're going to get.
Exactly. It's stochastic. The participants in this group are constantly asking themselves, is this a pattern? Wait, no. Is this a pattern? Maybe?
Now, if I'm betting on who learns the most, or at least who has the strongest brain signal, I'm putting my money on the correlated group.
The easy mode group.
Yeah. Their environment makes sense. They should be firing on all cylinders.
That is exactly what traditional learning models would predict. But Vaskovich and Torres found the opposite.
Really?
Yeah. When they looked at those micro-movement spikes, the noise, the mixed group showed the highest signal-to-noise ratio.
Hang on.
Yeah.
The group that was the most confused had the clearest signal.
Yes. The unstable environment provided the most opportunity for learning. Their brain activity was just through the roof.
Why? Is it because they couldn't just go on autopilot?
That's a huge part of it. In the correlated group, your brain gets lazy. It says, okay, I know the rule. I can stop paying close attention.
Right.
In the random group, your brain essentially gives up on finding a rule. But in the mixed group, your brain is hyper alert. It is maximizing its bandwidth to catch any possible clue.
It's like when you're driving in a storm. You turn down the radio, you lean forward, your eyes are darting everywhere. You're processing so much more information.
That's a perfect analogy. The storm of uncertainty forces the brain to open up its filters. But here is where the study gets really, really nuanced. The researchers noticed that inside that mixed group, the people driving in the storm, they didn't all handle it the same way.
The group split.
A clear divergence. Two distinct types of learners emerged from the data. Let's just call them type 1 and type 2.
Okay, so walk me through type 1.
Type 1 is your standard A student. The researchers called this the error correction mode. Their brain data showed very narrow variance. It fit that neat, symmetrical bell curve, the Gaussian distribution.
And Gaussian basically means normal, right? Standard.
In statistics, yes. It means their signals were all clustered tightly around a mean. They were steady. They acted like they were trying to fix a specific mistake to reach a goal.
It's like, I missed the target to the left, I'll adjust to the right.
Exactly that. And how did they do on the test?
They did it well, I'm guessing.
They crushed it. They had high scores on the explicit memory test. They could consciously tell you, oh yeah, I remember the pattern.
Okay, so that sounds like the winner. They figured it out. What did type 2 do?
Type 2 was the exploratory mode. And their brain data looked, well, it looked wild. It didn't fit a bell curve at all. It fit a gamma distribution, specifically in the exponential range.
Okay, you're getting technical on me. Gamma distribution in the exponential range.
Mm-hmm.
Why does the shape of the data even matter?
Because the shape tells us how they relate to time. The gamma distribution here indicates a process that is memoryless.
Memoryless, like they forgot what just happened.
In a statistical sense, yeah. It means that the past event wasn't predicting the future for them. They were living entirely in the here and now.
Okay, I think I follow.
Think about it like this. If you're an error corrector, type 1, you're carrying the past with you. Last time I did this, it worked, so I'll do it again.
Right.
But the type 2 explorers, they were treating every single moment as a brand new independent event. They weren't narrowing down. They were casting this wide net.
They were flailing, essentially.
Exactly. But wait. If you aren't using the past to predict the future, are you even learning? It sounds like you're just spinning your wheels.
That is the paradox. These type 2 learners had huge fluctuations in their signal. Their brains were processing a massive amount of information, high signal-to-noise ratio.
Yeah.
But
What?
they failed the explicit memory test.
They couldn't tell you the rule?
Nope. Low scores. They didn't consciously know the pattern.
So let me get this straight. Type 2 learners had brains that were working harder, exploring more, and processing more signal. But on paper, they looked like they learned less than the type 1s.
Exactly. And this is where the authors really drop the hammer on the traditional view. They argue that this exploratory mode, this memoryless high-variance state, isn't a failure.
It's a hidden phase of learning.
A crucial one. In fact, they connect it directly to how babies learn.
Babies. Neonates.
Yes. Think about a newborn baby. Have you ever watched them? They move their arms and legs in these jerky, random ways.
Yeah, the flailing phase.
For a long time, scientists thought that was just motor noise, an immature nervous system misfiring. But we now know that noise is the nervous system mapping its own body. The baby isn't trying to grab a toy. They don't even know they have a hand yet. They're asking, what happens if I fire this neuron? Oh, that moved. What about this one?
So it's not random, it's experimental.
It's spontaneous autonomy. They are mapping the space. And Vaskovich and Torres are arguing that the adult type 2 learners in that mixed group reverted to this baby-like state
Because the environment was so confusing.
because it was the smartest survival strategy. Think
Yeah.
about it. If you're in a chaotic, unstable world where the rules keep changing and you try to error correct too early, what happens?
You correct towards the wrong thing, you build a habit based on a coincidence.
Exactly. You get stuck in a local minimum. You find a solution that works okay for now, but you miss the bigger picture. The exploratory learners were smarter.
They kept your options open.
They stayed memoryless to gather more data before committing to a strategy.
So that feeling of being overwhelmed, that I don't know what's going on feeling, is actually your brain refusing to settle for a bad rule. It's staying open.
It's prioritizing curiosity over accuracy.
Yep.
It's maximizing surprise.
I love that phrase, maximizing surprise. It sounds so much more fun than minimizing error.
It is. But it's also expensive. It takes a lot of energy to run your brain in exploratory mode. You can't stay there forever.
Right, eventually you have to learn where the light switch actually is. Did the Type 2s ever figure it out?
They did. And this is the convergence. The researchers tracked them over time. Around block 8 of the experiment, so towards the end, those exploratory learners shifted.
What happened?
Their signal variance narrowed. That wild exponential gamma distribution morphed into the steady Gaussian bell curve.
The static cleared up.
They transitioned from purposeless wandering to goal-directed behavior. But, and this is the key takeaway, they only did it after they had fully mapped the space.
They self-discovered the goal.
So the type 1 people, the ones who aced the test early, they basically skipped the childhood phase.
They jumped straight to adulthood, straight to exploitation. I see a rule, I'm using it. The Type 2s spent time in childhood. I don't see a rule yet. I'm gonna play.
And the paper suggests that while the type 1s were faster, the type 2s were engaging in a richer, more robust biological process.
This makes me rethink so much about how we learn skills. I mean, think about learning a language or a new sport. We usually try to force ourselves to be Type 1 immediately.
What's the rule? How do I say this perfectly?
And we feel stupid when we can't do it. We feel like that noise, the stuttering, the mistakes is a sign of failure. But this research says no. That noise is the information. That is the sound of your brain building the map.
You can't check the map if you haven't drawn it yet.
Precisely. You cannot error correct a goal you haven't discovered.
The paper also touches on artificial intelligence. And this feels huge because right now AI is all about getting the right answer.
It is. Most machine learning, particularly reinforcement learning, is built on the error correction model. You define a reward, and the AI tries to get that reward as fast as possible by minimizing mistakes.
It's a type 1 machine.
It's a Type 1 machine, and that works great for chess or Go, where the rules are fixed. The board doesn't change.
But the real world is a mixed group.
The real world is unstable. If we want AI that can handle reality robots, that can walk on uneven terrain, or systems that can handle unpredictable markets, we might need to design them to be memoryless for a while.
We need to program them to be confused.
We need to program them to be curious, to value the exploration phase where the goal isn't to be right, but to maximize the signal, to just see what happens.
He needs a childhood.
It needs a childhood.
That is profound. It's weirdly comforting, to think that confusion isn't a bug in the system. It's a feature.
It's a high bandwidth feature.
So let's bring this back to the listener. If someone is stuck in that flailing phase right now, maybe they started a new job and they feel like they're drowning, what does this paper tell them?
It tells them, don't rush the Gaussian, don't rush to the point where everything is smooth and predictable.
Because if you force certainty too early, you stop learning. You stop seeing the nuance.
So embrace the gamma. Let your signal fluctuate. It feels chaotic, but that chaos is just your brain taking in a massive amount of data.
A convergence, the aha moment will happen.
But it has to come from the noise. You can't skip the noise to get to the signal. The noise creates the signal.
I feel like we should put that on a billboard. The noise creates the signal.
It's the truth, and it really challenges how we measure intelligence. Think about those Type 2 learners again.
The ones who failed the test.
Yeah. If you were their teacher, you'd say, they didn't pay attention. They didn't learn the lesson.
But their brains were actually working harder than the A students.
Exactly. We live in a society that measures explicit knowledge. Can you state the rule? Can you pass the exam? Can you do it fast?
But if we only value the people who jump straight to the answer, are we weeding out the people who are doing the deep structural mapping?
Are we punishing the explorers? I think we are. And in an unstable world, the explorers are the ones who survive when the pattern changes.
The error correctors crumble when the rulebook goes out the window.
But the explorers just say, okay, back to mapping. I've done this before.
It's resilience.
It is resilience.
This research really does flip the script. It takes static and turns it into dynamic process. It takes confusion and turns it into mapping.
And it takes failure and turns it into exploration.
And credit to Vaskevich and Torres for doing the hard math to prove it. I mean, it's not easy to analyze gross data.
Oh, it's way easier to just average it out and go to lunch.
Just average it out and go to lunch.
Yeah.
That's the temptation for all of us, isn't it?
It is. It's efficient. But efficiency isn't always the goal. Sometimes the goal is understanding. And understanding is messy.
Well, I, for one, am going to be a lot more patient with myself the next time I can't find the light switch in the dark.
Just remember, you're a dynamic stochastic process.
I'm not clumsy, I'm stochastic. That is it for this deep dive into the messy, beautiful way our brains learn. We will catch you in the next one.
Embrace the noise, everyone.
See you next time.